Hey everyone, hope you're having an amazing day. This is Sunil from Intel, and in this presentation I'm going to talk about the state of DMA offload for paravirtual I/O in OVS-DPDK. So let's see a bit in detail of what we will discuss today. First, we look at the problem at hand, where the bottleneck is today, and discuss on how DMA acceleration can help us solve this problem. Later, we will discuss how the OVS data path can be improved to make use of this DMA acceleration and how to make it scalable. In the end, we'll do a full packet walkthrough showing how the packets move from the NIC to the VM and back with DMA acceleration. So if we take a look at the PVP data path today, where the packet flows through the NIC onto the DPDK5 port, through the switching logic, and then to the vhost port, where the packets are then copied onto the VM. VM does some processing, after which the packets are again copied onto the host, and the packet all the way reaches the NIC back again. In such a comparatively simple pipeline, we see that a lot of the CPU cycles are being spent on just doing packet copy to and from the VM. Quantitatively, around 50% of the cycle spent on copy for large packets. 50% of the CPU cycles just doing copy in a switching application. This is definitely a problem we must address. But how do we address this? Is it possible to offload this copy onto some device that is specialized for copy? Well, yes, we can use a DMA. On many platforms today, we find that DMAs are already available. So let's see how we could make use of them here. Now, there are two ways we could use DMA devices: synchronously and asynchronously. In the synchronous offload, the CPU offloads some work onto the DMA and then waits for its completion. CPU does no other useful work in the meantime. But in asynchronous offload, the CPU, after offloading some work onto the DMA, can perform some other useful work in parallel. And after some time, can come back and check for DMA completions. This way, we can utilize both CPU and DMA to the full extent and should provide really good performance benefit. So let's take a look at how we can enable and utilize this asynchronous mode in OVS for our use case. Let's consider the southbound part first. That is to DMA offload the packets flowing from the VM to the host. Now, OVS is given the flexibility to configure and choose the DMA device and provides this information to the DPDK vhost library. The library then has two tasks at hand. First, to fetch and enqueue the packets onto the DMA device using the DMA dev interface in DPDK. And second, to poll for its completion sometime later, since we utilize the asynchronous nature of DMA. It's only possible to achieve both these tasks with a single interface because the RX interface is being polled continuously. So the packets that are enqueued to the DMA in the current iteration can be polled for its completion in the next one. This allows for CPU to do useful tasks in parallel while DMA is doing the copy. Let's take a look at the northbound part now. That is, DMA offload the packets flowing from the host onto the VM. OVS here again has the flexibility to choose the DMA device and provides this information to the vhost library. So it can take care of enqueuing the packets to the DMA. But what about polling for its completion? When and where could we do that? Unlike the vhost RX interface, OVS doesn't poll the vhost TX interface continuously. So we cannot make use of the idea to poll DMA completions for packets that we enqueued in the previous iteration. So how do we go about solving this? Well, based on the RFCs and input from the OVS community, the suggested design was to use this approach. As OVS already polls the RX interface for new packet arrivals, we can also use it to check for any DMA completions for the TX interface. By checking for DMA completions in this continuously polled part of the netdev, we can ensure that DMA completions are picked up quickly. So that's about the design on the interaction between the vhost library and OVS. But we haven't talked about how OVS is going to manage these DMA devices. OVS still has the responsibility to configure and assign the DMA devices. So how does the assignment scheme look like? For scalability reasons, we have a per thread assignment of DMA devices, which means no contention among threads to share the DMA devices. And since there are only a handful of them available, this is the best way to go about it from a resource consumption and from a scalability standpoint. So adding a thread in OVS implies adding a DMA resource. This allows for balance switch and copy performance as well. But this assignment scheme has its side effects. Let's see what those are. Having a DMA device per thread means a DMA device can be shared across vhost RX queues and TX queues. Things can get really messy if there isn't a mechanism in place to handle these situations elegantly. We came up with a solution to handle these problems inside the vhost library by having a DMA completions ring to mark the packet completions. More details on this could be found in the RF sales link below. Now, keeping all this in mind, let's now take a look at how the packet traverses through this modified pipeline. So like the usual case in PVP, the packet is received at the DPDK5 interface, then processed by the OVS to extract few critical information required for switching, and then forwarded to the vhost port to be sent to the VM. In this case, when the packet is received at the vhost interface, it's enqueued to the DMA and would ring the doorbell to initiate the copy. Once the DMA starts copying the packet, the CPU can do some useful work asynchronously in the meantime, like processing another packet. The second packet gets processed and is now enqueued to the DMA and is ready for copy. This is an example of how OVS can greatly benefit with the asynchronous offload. It enables the CPU and DMA engine to work in parallel. Now, this next phase in the pipeline is quite important since it involves multiple important operations. For simplicity, let's try to understand them one by one. Now, since CPU continues its operation in parallel, after some time in the pipeline, OVS polls the vhost RX interface. But hey, there is no work to be done here since there are no incoming packets from the VM. But remember, we also check for any TX DMA completions here in the same context. Now, the DMA copy initiated for the first yellow packet is complete. And when OVS checks for its completion, it's reported done. The vhost library then notifies the VM of a packet waiting for it to be consumed. Notice that during all this, DMA copy for the second packet has already started. Next, the VM sees and picks up the first packet and starts to do its processing. Meanwhile, the second packet is being copied by the DMA in parallel. Once the VM is done processing, it puts the packet back into the ring for OVS to pick up. OVS sees this, fetches the descriptors, and starts a DMA transfer of the packet. It's very important to note that this is now a packet coming from the VM to the host. The RX interface is also checked for any DMA completions, but there are none currently. Later, the TX interface is also checked for completions like before, and we see that the second green packet is now copied and ready to be picked up by the VM. As the DMA copy happens for the yellow packet from the guest to the host, the VM starts to process the second green packet. After a while, OVS again polls the vhost RX interface and finds that a packet is waiting for OVS to be consumed. So it initiates a DMA transfer for it and proceeds to check if there are any DMA completions. Turns out the yellow packet is copied by this time and ready for further processing by OVS. OVS then proceeds to check if there are any DMA completions on the TX interface. But this time there aren't any. Next, the received yellow packet is processed and then sent to its intended destination, the DPDK5 port. In the meantime, the second packet is copied in parallel from the VM to the host. After a while, the RX interface is polled again and the DMA is checked for any completions, and the green packet is reported done by now. OVS then proceeds to check for any DMA completions on the TX interface, but there are none. The green packet is then processed like the first yellow packet and sent to its intended destination, the DPDK5 port. So this captures the entire packet flow with the proposed design. Hope this walkthrough made things clearer. So what are our next steps? POC based on the presented design will be sent out to the community by 2.18 release once the required support is added in DPDK vhost library, and we request good support from the OVS community to upstream this design for the 2.19 release. Thanks to everyone who helped in creating this design. That's all from my side, folks. Thanks for tuning in. Reach out to us in case you have any queries. Thank you.
Welcome back, everyone. Let's thank our speaker for for giving the talk and for the work behind it. I believe that we have all three of the co-authors of this work available on the call. Sunil and Cian and Harry, would you like to say hi?
Hey, hi Ben. Can you hear me?
Yeah, I can hear you.
Hey. Hey, everyone.
All right, so we have two questions already. So the first one is from Aaron Canole, who says, you say OVS can choose a DMA device, but what does that mean? We don't currently have such knobs in OVS.
Sure. So this is a new knob that we are proposing to add so that OVS gets the flexibility to configure and choose which DMA device that it wants to use per thread. So that way OVS gets the flexibility to configure or do any changes in terms of DMA configurations that it likes or that it wants to use it in its way. And we can have any sort of automatic assignment, like I said in the presentation, we have a per thread assignment which provides us good scalability as well. So we can use that, use the automatic assignment. So to answer the question, yeah, so we are proposing to add a new knob to OVS to select the DMA devices.
Great. So Mike Patrick said in the chat, great talk, Sunil. And we have another question from Maxime Coquelin, who says, when XPS is used, several PMD threads will access the same virtual queue, and so several DMA channels will access the same virtual queue. Okay, so several PMD threads on the same virtual queue, and therefore several DMA channels on the same virtual queue. So in that case, how do you preserve the packet ordering?
Sure, that's a really good question. So when the threads actually access the same TXQ or any RxQ for that matter, so ordering is going to be a problem. So we need a mechanism in place to actually take care of this. Currently, we have proposed in the design. So there is a mechanism in place where we use a slot buffer array, which can tell us when the DMA completions are done, we can mark them. And that sort of provides us an in-order kind of a pattern where we can simply count the completions later to provide information on how much of DMA completions are being done. So even though DMA completions can be reported back, in a different order, but that array will make sure that the reporting or the counting, etc., is being done in the in-order way. So there is already a patch on the DPDK mailing list, which actually sort of describes and implements this design. I think I've posted a link to that in the slide deck. So please do go through that. It might help explain things better.
It's great. It's good to have that detail. Would either of the other co-authors like to say anything?
So I guess just to expand a little, sure. I guess to expand a little on what Sunil mentioned, that reordering of completions is essentially a feature that we can provide as part of the DPDK vhost library. What that means is that it's not OVS code that's going to be handling this particular complexity, and it can actually be provided by DPDK and the internals of the vhost library. I think that is ultimately one of the goals, and I believe Jiaju Yu from Intel also, who works extensively on the vhost APIs in DPDK, and Maxime, I know you were involved as well in some reviews and discussions around this, so thanks for your support there. And this really is a community effort all through the DPDK stack, the DPDK DMA dev enabling that went on in the last releases, the OVS community providing feedback and influencing that design right from the hardware access libraries, which is DMA dev, all the way up through vhost and into OVS, into how that gets integrated. So this is a big effort, but look, we really appreciate the community's support here and integration, and looking forward to getting more feedback and more discussions in place. Let's keep reviewing, keep making progress, and then ultimately get these things deployed into OVS, vSwitch D instances, so that your vhost performs better. Thanks.
Thanks for that extra insight. We do have one more question here from Aaron Smith, who asks, can DMA and regular copies be mixed?
Sure. So regular copies, I think, mean CPU copies. So they can be mixed, but the ordering, I think, becomes quite important there. So I think if we preserve the order, yes, we can definitely mix DMA and regular copies.
And is there a practical way to preserve that order?
Yes, that should be taken care inside the library itself. That the management of that should be taken care inside the library. So OVS at an application level need not be bothered by that level of detail on how the vhost library is going to take care of it. So yeah, so there is a mechanism, there is a way to handle both DMA as well as CPU copies as well. Yeah.
Okay. We are a few minutes ahead of schedule, so if any of you has further comments, then we have time for that. Otherwise, we'll move on to the next talk.